This video is showing the results of a study conducted on a selected residential villa in Dubai and implementing strategies to reduce its annual electricity demand.
In the past, the people in United Arab Emirates found suitable solution to resist the hot climate inside the homes. They produce a practical and effective solution to achieve a comfortable level, despite of the high temperature and humidity. After the 1950s and after the oil discovered in the area, the transition period began, and the way of achieving comfortable level change from traditional concepts and methods to electrical devices such as air conditioning and ventilation. In the past, before 1950s, people used different concepts and different material that helped them to reduce the negative impact and to overcome the hot climate. Traditional homes used different material that was due to the three types of ecosystem available in the United Arab Emirates: the desert ecosystem, mountain ecosystem, and coastal ecosystem. For example, in the desert area, palm trees were the majority of plantation at the time. People used to build their homes from palm leaves and they call it al-arish. Same concept in the coastal area. The main material used is coral, while the mountain area people use stone material for buildings. Residential building, villa in Dubai, and by learning lessons from the past and investigating the optimal solution of energy demand reduction by using simulation systems, which is IES. In this study, we'll go through the past and the present existing architectural design and environmental build in order to achieve the following. First, to develop timeline of architectural design concept in terms of sustainable build over the time, past, present, and the future. Also, we have to check the possibility of implementing passive cooling concept in the existing building. Third, implement modeling energy of the existing building with selected options. Finally, to define most three effective passive cooling concepts for the existing villa. Moving from the past to present, due to the oil discovery and economic flourishment that happened, building material changed to mostly concrete. Population of the country increased and there was a huge demand in the housing, and different aspects result to almost neglect the sustainable concept design and to be replaced. Also, this caused increase in the electricity load of the homes due to the hot climate in the country, most of the energy being used for cooling the building. The concept of building design started to take a new direction towards sustainability, aiming to achieve carbon neutral homes. The new government direction and world attention to climate change give the strong support for building section to reconsider the sustainability. Carbon neutral homes is a new trend in architectural design in the future homes. The combination of past concept and present technologies helps to develop a new pioneering concept that will achieve the carbon neutral homes goals. In the future homes, there is many elements to be have available, which is contain passive cooling, green area, smart systems, well insulated and sustainable materials. Recently, many studies focus on passive strategy. The implementation of various passive strategy in the region help us to understand how will energy will be reduced from the implementation such a strategy. Dr. Hanan Talib 2014 consider that the passive cooling will be achieved if all main element of design building works as shield to gain the solar heat and able to save the cooling inside the building during hot seasons. By implementing the passive cooling strategy in Dubai villas such as shading, double glazing, natural ventilation, green roofing and insulation can help to reduce the load of cooling by 9% and the annual electricity by 23.5%. Fist and Action 2017 shows that the implementation passive measures to building envelope can reduce the energy footprint in United Arab Emirates building, and there is a big chance to improve the existing building energy as well consumption by implementing retrofit strategies. The ordination of the windows can play a major role in energy reduction, which reach up to 55% of cooling load of the homes and villa. Courtyard also can help to reduce the amount of energy by 8%, as it will allow the natural ventilation for villa. External shading vegetation can be considered as an effective solution to reduce the energy consumption up to 34%. In this study, the methodology consists of 3 stages. The first stage is literature review. It's talking about the past history of houses in the UAE, present how the houses are being built nowadays, and the future. The study focusing on the passive strategies. The second stage is site visit and interview, evaluating the current condition of the villa and the energy consumption details during the 2021. The third stage is a software simulation and consisting 4 strategies, each strategy having 3 scenarios, and the shading device is the first strategy, insulation material, glazing and windows, and the last strategy is roofing cover. The best case study selected from United Arab Emirates, Dubai, and it's a private villa with a plot area 10,000 square feet and the build-up area 5,900 square feet. Consists of 2-story and 1 building as attachment connected with the villa by a closed corridor. The electricity of a period 1st of Jan till 31st of December 2021 was our baseline, as well as water consumption for the same period. In this study, the weather of Emirates of Dubai considered as our baseline, to include the average sun hour and sun day, the average rainfall, and humidity.
The base case was modeled in IESVE software using Modelit application. The construction layers were assigned based on the information obtained from the consultant as well as the AutoCAD drawings. The U values were set as shown here. Annual profiles were created by following the occupant's behavior. Internal gains of humans and lighting were added to the model as well. After adding all the details, the solar radiation analysis was carried out. To check the simulated model accuracy, the total electricity results were compared with DEWA bills for the period of 1 year. After having the validated base case model, each defined strategy with its scenarios were implemented on the base case model. The proposed strategies and scenarios were designed to meet the requirement of SAFAT building regulations by Dubai municipality. The simulated results were very close to the existing conditions and had only 1% difference. By referring to the literature, it is accepted to have up to 5% error from reality. Therefore, the base case model was validated with 99% accuracy, which can be considered as a good validation. This strategy was designed to reduce the energy demand by adding insulation to the existing external walls and roof. After checking the different products, the insulation with the shown details were chosen for implementation. The first scenario was adding the insulation to the external walls. The construction layers of the external walls were modified and added the insulation material to reach the shown U value. By applying this insulation on the external walls, the reduction in total annual electricity was more than 20 megawatt hours, which is around 24.5% from the base case. The second scenario included adding the same insulation material to the roof, which resulted in almost 15.5 megawatt hours reduction in total annual electricity from the base case model. This is around 90% from the base case. Both tested scenarios showed good reduction in total annual electricity. Therefore, the third scenario evaluated the reduction resulted by applying the insulation in both roof and external walls. This scenario resulted in 55 megawatt hour reduction in total annual electricity, which is almost 45% reduction from base case model, which is significant. Strategy 2. This strategy is testing 3 different scenarios for the glazing and evaluating the change in the total annual electricity demand for each scenario. Scenario 1. First scenario depended on using the same existing windows and only applying a film on them. The chosen film had U value of 2.5. After applying this film, the total U value for external windows was reduced from 1.8 to 1.5. By having this change, the total annual electricity was only reduced by less than 1%, which is not a noticeable number. The second scenario considered changing the glazing to another insulated double glazed with keeping the same existing frames. The proposed type was Guardian Glass SunGuard SN50T with the glass U value of 1. After using this type, the total window U value was reduced to 1.3, which is less than scenario 1. After the Apache simulation, the total annual electricity was also reduced by 5.5 megawatt for the entire year, which makes it more than 6%. This scenario had more reduction than the previous one. Scenario 3 was changing the external windows type completely to triple glazing. The total U value for the proposed triple glazed windows was only 0.8. The total annual electricity reduction caused by this scenario was 7.5 megawatt hour for the entire year, which is 9% reduction from the base case model. Strategy 3: Shading. This strategy, the proposed scenarios test methods to reduce the solar heat gain, which causes the increase in electricity consumption, by reducing the direct solar radiation on the building. The first scenario focused on the window opening and proposed a modification to the existing window. Since the existing windows has a projected decorative element, the shading device is designed to be added on the existing one with extending it 15 cm to keep the same visual appearance and using the similar materials. By applying this scenario, the reduction of total electricity was very minimal. It was less than 5% annually in the total electricity. This percentage of reduction is not considered as a feasible way to be applied in the existing model. Another simulation was carried out on the same model of the previous scenario and extended the decorative element on the edges of the villa with the same extension of 15 cm. And this was applied on the same IES model which had the extended windows. This scenario resulted with only 0.6% reduction in the total annual electricity, which also is not practical to be applied. Therefore, the shading device strategy was eliminated from this study. The third scenario was created to add trees in the landscape. The chosen trees are similar to the same existing trees and the number as well. This resulted in almost 1.5% reduction in the total annual electricity of the villa. After eliminating the shading devices from the windows and the edges of the video, a third scenario was created to test adding trees to the landscape. Strategy 4. By referring to the solar radiation analysis from Suncast on the base case, the rooftop is having the highest solar radiation. Therefore, options for covering the roof was investigated. Scenario 1: covering the majlis. This part can be covered by a pergola to create an outdoor seating area, as well as cover the roof of the extension of the villa from the direct solar radiation. This scenario started by implementing the pergola on top of the majlis area only, keeping the pergola height with the same level of the facing windows. Suncast analysis was done and the Apache simulation was carried out. This change resulted in 2% reduction in the annual total electricity. Since 4% is not a big noticeable reduction, however, creating a pergola for outdoor seating in the rooftop was part of the owner's plan. Therefore, this is considered for the final implementation. Furthermore, the third scenario tested the effect of adding PV panels on the same proposed pergola. The second stage studied the impact of covering the full area of the upper roof as well. by choosing the wide open parts on the roof and avoiding the narrow areas. After modeling it in the Model It application, the suncast analysis was carried out and Apache simulation was conducted. The result of the total electricity in this case showed reduction of more than 4% from the base case. The chosen PV panels are monocrystalline with the module nominal efficiency of 29%. The panels were arranged facing south with the tilt angle of 22 degrees, the optimal tilt angle for Dubai, as defined in the literature. Total of 48 panels used to cover the roof area. Calculation of the annual PV generated electricity showed almost 50 megawatt hours production, which is a noticeable number. This means 59% of the total needed annual electricity are generated by these panels. Considering the amount of electricity bill reduction per year will be around 5,500 dirhams from the total approximate 9,000 dirhams. Considering the initial cost for these panels, each panel costs around 700 dirhams, making the total of 33,600 for the used panels. The payback period, considering the savings from the electricity bills, will be around 6 years. This calculation is made without considering the maintenance and other costs, which will increase the payback period. After testing the various scenarios, the following scenarios were chosen for modeling the optimal case: implementing the roof and wall insulation, changing the existing external windows to triple glazed windows, covering the roof, and adding PV panels. The optimal case was modeled by implementing each of the mentioned scenarios and measuring the reduction caused in each stage. Then the final model with all the best scenarios were achieved. In this final optimal model, the amount of annual electricity reduction achieved was significant. Almost 50% from the base case model was achieved. Comparing these results with the literature, this research achieved more reduction in energy demand than the mentioned literature. Additionally, the amount of the PV electricity generated is exceeding the needed electricity after implementing the scenarios. In this case, the number of PV panels could be reduced, therefore the initial cost and the payback period could be reduced. Also, in other countries, there is the possibility of returning the extra electricity to the grid. However, this option is not implemented in UAE. In conclusion, this research aimed at examining various strategies and scenarios to reduce the annual electricity demand of a selected residential villa in Dubai. Simulating the scenarios through IESVE software was the main method adopted for examinations. The base case model was validated with 99% accuracy from reality. Finally, the best scenarios were then selected and implemented together to check the change they caused to the base case model. The achieved reduction was around 50% from the base case model, which is considered significant. As future recommendations for this research, since this study aimed mainly at reducing the total annual electricity, the change in daylight factor was not considered. It is recommended as a further step for this study to consider the daylight factor and measure the changes it is caused, especially in the scenarios concerned with the external windows.